Okay, so 8.4, using exponential functions. All right, again, you got to make sure that you understand the concept or understand what the look is of a growth and a decay. And remember, the whole key is the output, the output, the output, the output, the output. What's happening to the output? And again, what's happening in the output as the input increases? As you move left to right in the graph, what does the output do? Because left to right, all right, in algebra, it's just numbers, from negatives to positives and bigger positives, right, as you move left to right. But in real life, maybe it's time. And so you're increasing in time. Distance. It can be all different kinds of things, but you're always looking left to right. So as x increases, y increases the output, and so that's what a growth is. Right? As x increases, then y increases. It's lousy writing, but it's increases. This is, whoops, prop, that's good. Population does this. Bacteria. Be nice if money, compound interest. And actually, all three of these examples can, except for compound interest, can go the other way. But again, as you can see, as you move from left to right, hey, what's happening? The function is increasing. The output's getting bigger. So we're increasing, we're going up, up, and away. Again, we talked about some of these aspects on Friday. So exponential decay is just the output decreases as you increase the input. Again, as you move left to right, right? Moving left to right increases the input. What happens? The output goes down. Radioactive decay. Again, bacteria population. There are some other examples. You got growths, you have decays, and we've got to be aware of both. Growth, decays, and be ready for both. All right, I'm going to go fast here because we talked about these things on Friday. Again, your basic patterns. So 2 different ways we can represent the base. Don't get hung up on this. And by the way, you guys have to, if I'm going too fast or if I'm seemingly passing up something, let me know, because I'm doing the exact same things in Algebra 1 right now. We're covering the exact same concepts. Algebra 2, we're taking it a little bit farther, but the exact same concepts. So remind me or stop me if I'm going too fast, because I may be thinking, all right, I just said that like yesterday, but maybe it was Algebra 1 and not Algebra 2. Okay, so 2 different ways of representing the base. The base is called the growth factor. I think we did this in here on Friday, did we not? Am I thinking the right place? Yes? Okay. Yes? Yes. Right before talking about the compounding formula. All right? So again, the base is the growth factor. In the first example, it's the 1 plus r. In the second, it's the b. If you were looking at the compounding formula, right? You just need to write it. That was the 1 plus r over n, right? That would be the growth factor, all of that together. All right? And then r, that's the pirate r. And then r is simply the rate of change. And oftentimes that's given in percent form. Could be a percentage rate, all of those different situations. And look, the bottom line is, when you add up everything that is the base, whether it's 1 plus r over n, or just the b, when you get down to what the whole base value is, if the whole base value is less than 1, then this is going to be a decay. Anything less than 1 to any exponent is going to give you a smaller output as you increase the input. However, if all that base together ends up being greater than 1, then it's going to be a growth. All right, again, not going to spend much time because we did introduce all that stuff the other day. I just want us to get decent at applying it to functions. You guys got to get used to looking at a function and understanding what things mean. Okay, one other aspect of base is called the growth factor. I think, did we say growth factor last time? Yeah, we did. All right, so good. All right, so look, you're looking at a function, right? And your thought should say, oh, that's an exponential function. Why would you say that? Because the variable is an exponent, right? Here the variable t is an exponent. We have f of t. You could have just as easily had y, right? Because f of t and y are interchangeable, and you've got a function, and you have an exponential function. And so because you have an exponential function, you should easily be able to tell the initial amount, and it is 2,000. All right, we wrote this Friday. If you need to write it again, remember the initial amount is the a value, the multiplier, right? All right, so think for a second. So for example, which really should be a instead of number 1, but who cares? The growth factor is 3.5. How did you get that? 1 plus r. All right, it's the whole base. Whatever the whole value of the base is. 1 plus 2.5. Johnny and Sally is 3.5. All right. What is the rate of change? The rate of change is just the r. So what's 2.5 in percent form? So you could say 2.5, or if you want percent, it'd be 250%. Sometimes they'll just want it in decimal form, and sometimes they'll want it in percent form, right? 2.5, again, go back to pre-algebra. How do you change the decimal into percent? Multiply times 100%, or move the decimal point 2 places to the right and put a percent symbol, right? I mean, 2.5. It's 250%. Is this a decay or a growth? All you're really looking at is the fact, if the growth factor is bigger than 1, it's a growth. If it's less than 1, it's a decay. 3.5 last time I checked is bigger than 1, and so it's a growth. And we get all that from the function. And we get that because we know the multiplier is the initial amount. We know the total base is the growth factor. And from there we can get everything else. Okay, so what about this second one? Just run down and write in your amounts. I'm going to write them as you're writing them, but if I were you, I'd think and see if you can write them instead of just looking. And I hope you wrote 32,000. 0.25 is the growth factor. How did you get that? 1 minus 0.75. What's the rate of change? Negative 0.75, the R value, which is negative 75%. And then because the growth factor is 0.25 and less than 1, it is a decay. Again, if you have questions, please ask, and I'll explain more fully any of those. All right, do it again for the next one. Again, if you can avoid looking, avoid looking. All right, I think the only debate is what you're going to put for the rate of change. And hopefully you're going to put 0.5, right? Or 50%. Because it's 1 plus R. All right? How did you get 1.5? You must have added 0.5 to 1, right? Because the rate of change is R, Alex.
So if the function is f of t, shouldn't the variable be t not f?
Yeah, it should be a t. Very good. No Kool-Aid for you. I think the next one's the same way too. That's what happens when you copy and paste. All right, so last one. Go ahead and finish the last one off. Initial amount, growth factor, rate of change. Okay, that one's got a big growth factor, right? I mean, 7 to the first is 7. 7 squared, you're already up to 49. You're really taking off. And then you got a 5 multiplier to boot, and that thing's really shooting up very, 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 very fast. Again, what's the rate of change? 1 plus 6 must have been the base, right? And what is 6 in percent form? 600%. Right. I see no hands, so I'm rolling on. Okay. So here we see a similar type function. The only difference is the base is e, and we're going to talk about e in the second half of the chapter. So if you looked at this, c would represent what? What is c going to be? Come on, talk to me. What is c? What does it represent? The initial amount, right? And that's exactly the case, because we know the pattern now. At least you should know the pattern now, right? C is the initial amount. It's an exponential function. There happens to be a multiplier of the variable, but that's okay, and not an issue. So there are 300,000 people in Heritage Town. How long will it take for the population to double? By the way, I think you guys have a money sign up there that you need to scribble through, which I got rid of on my presentation. So in this situation, we need to solve this for when the population doubles. Now, we want A to be what in respect to C if the population's going to double? For example, let's suppose the population was 1,000. What would A be? 2,000. In our example, the population is 300,000, so A must be 600. Wow, you guys are so smart. All right, so 600,000 equals 300,000 times e to the 0.2t. Now, you could have done this problem if I didn't even tell you that there was 300,000 people. You're like, no way. We had to know the initial amount of people. All right, remember, exponential function, we have to isolate the base with its exponent before we can continue. So we need to move the 300,000, and we move it just like always. Things multiplied times a variable, you multiply by the reciprocal, or you divide both sides by the 300,000. Newsflash, what is 600,000 divided by 200,000? 2. And what are we doing? We're doing a double. What'd I say? Whatever. Whenever it doubles, the A divided by the C is always 2. Look, if we said triple, who cares what the initial amount is? We're looking for a time, and the A divided by the C would be a 3 if it was tripling. If it half, maybe it's a decay, and how long it would take for the population to decrease by half, then the A divided by the C is going to be a half, and you don't really need to know the initial value. If I had time, and I'd love to do it, way back, When my wife first started working, she started getting some savings bonds, and back then, savings bonds, you would buy it for half the amount. So if you want a $100 savings bond, you would pay $50. And it would be face value in about 7 years, a doubling, time it took to double. And you can run the problem and figure out what would then have been the percentage rate for it to double in 7 years. And it was like 9-point-something%, which was really, really good, especially being they're giving like 0.001% in the bank right now. And if you were in Europe, they're giving you -% in the bank, which is really awesome. All right, let's finish this problem. You guys have no idea what to do next. We're going to learn this next chapter. We're going to take the natural log of both sides. Go ahead, you can write that in. Natural log of both sides. ln, that's a script ln. Yeah, it's pretty ugly looking, sorry. A script ln. You're going to find your calculator button in a minute. Here, we got to hurry up, so let's roll. So now we have the natural log of 2. And believe it or not, you don't know this, but the natural log of e cancel each other out, and so the other side is 0.2t. So now we have the natural log of 2 equals 0.2t. And again, we're going to deal this in detail in the second half of the chapter. But algebra from here, you know, to simply divide the left by 0.2, right? So take your calculator out, find your natural log button, it's on there. Do the natural log of 2 divided by 0.2, and we'll finish off this problem and roll on. You have an ln button. You should have gotten like -1.609 divided by 0.2. And what in the world did I just get? Yeah, I don't know what my calculator just did. 0.693. There we go. Does crazy things sometimes, or it's operator error. 3.5 would be the answer. And what are we in? We're in years, and so this is 3.5 years. Would it take the population of Heritage Town to double? Don't worry about your button. We'll play with it a lot in the second half of the chapter. Again, don't worry about your button. If you didn't find it, it's not going to be an issue. Okay, there are 2,000 bacteria. If T is in hours, how many bacteria will there be in 4 days? This one's a straightforward problem. So we're looking for A because we're looking for how many bacteria. Initial amount, 2 grand, right? We're going to use E. You'll find your E button as well in a minute. And then what do we have? The point, whoa, wrong pen. To the 0.2, and T is in hours. So the only trick in this problem is 4 days is how many hours? So hopefully we all know to take 4 days and multiply it times, I would hope, please don't scare me. So you have to do E to the parentheses 0.2 times 4 times 24. Close the parentheses. Multiply that value times 2,000. So you have an E to the X button. It's there on your calculator. E to the X. And again, some of you have to put in the 0.2 times 4 times 24 first, and then do E to the X. Others of you have to do E to the X button first, then parentheses, 0.2 times 4 times 24, close the parentheses. Multiply it times 2, and you can see there's a lot of bacteria. 4.36 times 10 to the 11th. That's 436 billion. 436 billion. 436 billion. I got news for you. Before you can see mold, you want to know how many? No, there's like, it's billions and billions and billions and billions and billions before you ever see it. Billions and billions and billions and billions and billions and billions. Man, I don't have enough time for my favorite part. Oh, I'm so bummed. Radioactive decay. All right, quiet, because I'm going to teach you something here in the last couple seconds. All right, radioactive decay formula is similar. When you think of radioactive decay, you have to think of Half-Life, not the video game. I don't even know if it's popular anymore. This top T is time, and the bottom capital T is the half-life. Half-life is the time it takes for half of the substance to decay away. Half-life, the time it takes for half of the substance to decay away. The negative in the T gives you a decay curve, right? And that's what you would expect, the time it takes for half of it to decay away. All right, so take a couple minutes here and teach you basic radioactivity. There are three kinds of radioactive particles. One are gamma rays. Gamma rays are very energetic. They'll go right through you. If there's a lot of them, they will vaporize you. You will be gone. Sayonara, hasta mañana. If there's not that many, they'll burn your eyes out and whatever, so they're not good. All right, it's the initial light flash. They move very, very fast, very, very energetic, and it's very, very bad. The other two are particles that are way heavier. A beta particle isn't as heavy, but it's basically an electron that's no longer going around the nucleus, but it's buzzing through everything and just flying through. It'll go through you as well. What will happen is if it hits your DNA, it can cause your DNA to malfunction. And when your DNA malfunctions and it replicates itself, there's a malfunction in the replication, and we call that cancer. The other is an alpha particle, which is bigger. It's the same as a hydrogen, but it's a hydrogen ion, those of you with chemistry. A sheet of paper can stop an alpha particle, but if you ingest the alpha particle, it really messes you up, because it's in there and it messes up a lot of DNA. And again, messes up the DNA. When the DNA goes to replicate, it doesn't replicate properly, and therefore you have a malfunctioned cell in your body, and that's cancer. Right? What do you have? What did somebody say? Whatever. All right. So here's basic radioactivity chain. You have the substance, I think it's thorium, TH, 232. The top number is what's in the nucleus. What's in the nucleus of an atom? Protons and neutrons. All right. So it's total 232 protons and neutrons, of which 90 are protons. The bottom number is the number of protons. Tells you what it is, right? Why is oxygen oxygen? Because it has 8 protons. Yeah. Why is nitrogen nitrogen? Because it has 6 protons. Any atom with 6 protons is nitrogen. Any atom with 8 protons, you guys know this, right? Oh my, so you don't know that a substance is a substance because of the number of protons? You're scaring me. Okay. You're scaring me. All right. It's the number of protons that makes the substance a substance. All right. Regardless. Alpha decay. This substance undergoes alpha decay in a certain amount of half-life. I don't remember the time. I didn't write it on this one. So, and it undergoes alpha decay, meaning an alpha particle is spit out of the nucleus. Spit out of the nucleus. All right. Alpha particle comes out of the nucleus of this, which means 2 protons are gone. Therefore, now in the nucleus you only have 88 protons, and that substance became radon, which is still radioactive. And you lost 4 of the protons, neutrons, so the top number now is 228. Top number tells you the isotope, which one. That also gives off a bunch of gamma rays in the radioactive decay. Okay, so now you have an alpha particle out there, but radon undergoes beta decay. And so it spits out an electron out of the nucleus. Wait a minute, does that strike anybody as funny? An electron out of the nucleus? What's in the nucleus of an atom? Protons and? How did an electron get in there? Would you believe that a neutron, quote unquote, split into a proton and an electron? Would you believe the mass of a neutron is a little more massive than a proton? Do you guys know about quarks? Up, down, left, right, charm, strange? Quarks? Okay. Very quirky subject. But here's what happens. If a neutron became a proton and spit out the electron, you now, instead of having 88 in the nucleus, you now have 89, and you now have the substance actium, not actinium. And we have still 228, and I could do the rest of the chain here. Believe it or not, you get back to thorium here, which is 90 and 228, because we get one more beta decay. And there's these decay chains, and I'd love to speak more about it and show you the nuclear fission and stuff, but I don't have time. Let me finish off with this. What's the half-life of carbon-14? 5,730 years. Anybody know anything about carbon-14? It's used in what? Carbon dating. It undergoes beta decay, and it decays into nitrogen. I want you to look at this curve. Exponential decay, right? What are we approaching? 0. Look way down here. It's 50,000 years. You know how little change in percent to change down here? It's flat down here, right? Any little itty bitty bit of change here changes this millions of years. Millions of years. Millions of years. And yet they want to claim that radiocarbon-14 dating is so accurate. Well, maybe up in here, not down in here. All right, do the homework. Quiz on Wednesday, test on Thursday.
Right away.